at let's say at dispersion over a complex terrain, yeah, we have to consider that the fate of these emissions will be affected by a lot of atmospheric processes working at different spatial scales. And in particular, we'll see different between nighttime and daytime. And most of these processes are connected to the interaction between the atmosphere and the orography. And this interaction can encompass both mechanical effects, so for example, channeling of winds inside valley and so on, but also thermal effects, because we will see later that in most of the cases in complex terrain, we have the development of the so-called thermally driven circulations, which are driven by thermal contrast between different parts of the valley or between different parts of the topography. Here in this slide, you have, let's say, an example of what can happen during night, and then we'll try to see these effects more in detail. But during the night, usually we have the development of cold air close to the surface, of course, due to the cooling of the surface itself. And this can drive the presence of a stable stratification. And as you probably know, stable stratification means that we have reduced vertical motion, and so we have reduced capacity of the atmosphere to induce dispersion. And then, as we'll see later, we have also the development of this downslope flow, which can, let's say, influence the transport of pollutants inside complex terrain. If we move during daytime, we have more or less the opposite situation. And this is, let's say, true also, of course, over flat areas that we have contrasting meteorological conditions between day and night. But we can say that over mountains, these contrasts can be enhanced, as we'll see later, due to the differences in this thermally driven circulation and also due to the presence of stronger thermal inversions with respect to flat terrain, for example. So during the day, we can have the opposite situation. If during the night we have this downslope flow, as we will see later, during the day we have the opposite, so this upslope flow, so flows which are generated, for example, by the heating of the slopes due to the presence of solar radiation. And of course, during the day, as it is true also over complex terrain, usually we have more convective mixing due to the heating of the surface. And so we have also, let's say, more efficiency of dispersion. We have a higher boundary layer during the day with respect of the nighttime conditions. As I was mentioning before, one of the, let's say, peculiar, let's say, aspect that can affect pollutant dispersion over complex terrain is the development of very strong thermal inversions. Of course, thermal inversion, as you probably know, is an increase of temperature, which can be, for example, close to the surface, as in this picture. So in this case, it is called ground-based thermal inversion, or can also be present some elevated layers in the atmosphere. In that case, we can talk about elevated thermal inversions. But yeah, thermal inversions, in particular ground-based thermal inversions, of course, are usually present also over flat terrain, so over simple terrain due to the cooling of the surface, and so the progressive cooling of the atmospheric layers close to the surface, starting from below. And as you know, this is conditions in which we can have accumulation of pollutants close to the surface due to the reduced mix. So it is, let's say, an unfortunate condition for pollutant dispersion. However, over complex terrain, in particular over inside valleys and inside basin, usually thermal inversions can be stronger, and also they can last longer than over flat areas. So over flat areas, usually thermal inversions are dissipated during the day due to the arrival of solar radiation. However, especially in winter and in narrow valleys, due to the reduced incoming solar radiation, thermal inversions in valleys and basins can persist also during the day. So with these effects of accumulation of pollutants, as we'll see later. Another aspect that should be taken into account is the presence of this downslope flow. So during the night, we have the accumulation of cold air close to the mountain tops or close to the slopes. And this cold air, of course, since it is heavier than the surrounding air, will start to flow down the sidewalls. And so this cold air will progressively accumulate in the lower parts of the valley floor and the lower parts of the basin. And this, of course, is a situation in which we can have a strengthening of the thermal inversion. So these are the main reason, very briefly, why we can expect stronger thermal inversions, and so bad condition for pollutant dispersions over near the bottom of valleys or near the bottom of mountain basins. And again, you probably already know what can be the effects of thermal inversions on pollutant dispersion. If we have an inversion, cold air is trapped underneath this layer with warmer air, and so the smog also is trapped close to the surface because vertical mixing is inhibited. While if we have, let's say, a sort of normal stratification of the atmosphere, so with a more unstable atmosphere, we can have the development of vertical motions, and so we can have a stronger mixing of pollutants. This is an example of what can happen inside a mountain valley. So we are here in the city of Bolzano again, in South Tyrol, so in the northern part of Italy, at the bottom of a rather narrow and deep alpine valley. And these are measurements taken with a temperature profiler in December 2016. These are the average vertical profiles of temperature at different hours of the day. So a sort of diurnal cycle, daily cycle of the vertical profiles of temperature. You can see that the colors identify different hours during the day. And it is clear that during the night, we have the development of a rather strong thermal inversion with this increase of temperature in the layers of the atmosphere closest to the ground. So in particular, if we look at the nighttime hours or in the morning, these blue and green colors, you can see the strong increase of temperature between the surface. So here we are more or less 200 meters above sea level and more or less 900 meters above sea level. So we have a deep layer characterized by the presence of ground-based thermal inversion. Then if we look at the central hours of the day, so here we are in December, so we have sun just for some hours during the day, you can see that starting from late morning, so 10, 11, and noon, we have the development of very shallow mixed layer close to the surface. You can see here this change in the stratification close to the surface due to the arrival of solar radiation and so to the warming of the surface itself, while the inversion persists at higher levels because in winter the warming of the surface is not able to mix the whole thermal inversion. So let's say just the layers closest to the surface are affected by the heating of the surface itself, while the thermal inversion, in this case an elevated thermal inversion, persists also during the day in the elevated layers. Sorry, I have the phone. Okay. Then after, let's say, starting from mid-afternoon, we have, of course, sunset. And so if we go to the orange and then the red colors, you can see the progressive development starting from here of the new, let's say, thermal inversion, ground-based thermal inversion due to the cooling of the surface. So you can see the thickening of the layer affected by the thermal inversion during the afternoon and then the evening, and so then we have the new cycle with the strong thermal inversion during the night, and then the at least partial breakup of the thermal inversion during the day. And the same, let's say, the same type of the daily cycle can be visualized in this time height plot. So on the x-axis, we have time. Here, this is a particular day in January 2017, while on the y-axis, we have a height above sea level. The red colors represent a positive temperature gradient. So it means that we have a thermal inversion, so we have an increase of temperature with height, while the blue part of the graphic represents a negative temperature gradient. So we have a decrease of temperature with height. And it is clear that during the night, we have, in particular, if we start here in, let's say, in the afternoon, after sunset, we have the progressive development of this thermal inversion, which is thickening during the evening and then the night. And during the night, we have this, let's say, deep layer affected by an increase of temperature with high, so affected by the thermal inversion. And then during the day, starting from the surface, we have the progressive breakup of the thermal inversion with this mixed layer, which is increasing during the day. And then just for a couple of hours in the early afternoon, we have that the whole atmospheric layer is not affected by the presence of the thermal inversion. And again, what are the effects of thermal inversions? We have this layer with stagnant air with weak vertical motions. And as a consequence, we can expect the trapping of pollutants close to the surface. This is an image of a city in which it is clear the presence of this polluted air below a certain level, probably the level affected by the thermal inversion, and then above or affected by weak mixing, and above cleaner atmosphere. And the same can be seen from this other image in which you can see a plume which is emitted by a certain source, which rise a little bit in the atmosphere due to probably to the presence of initial buoyancy, initial temperature, which is higher than the surrounding atmosphere. And then when it reaches a certain equilibrium level, the plume is not able to have vertical motion, and so it remains stratified in a certain layer due to the presence of weak mixing and probably thermal inversion. Here, another example of what can happen, the relation between the thermal stratification and pollutant dispersion. Here, we perform some measurements, again, in Alpine Valley, here in the Alps, of temperature and PM10 concentration. These are some vertical profiles of temperature at different hours of the day. This was in early spring, in March. And we had the presence of a thermal inversion, as you can see, at 8:30 in the morning. So you can see that in the lowest 200 meters above the surface, we had this increase of temperature with height. Well, then during this day, we had a progressive mixing of the atmosphere. So due to the arrival of solar radiation, we have a more, let's say, typical or normal temperature profile with a decrease of temperature with height. And if we try to connect this temperature profile with the measurements of PM10 concentrations, you can see that here, in particular in the morning, we have this strong increase of pollutant concentration, in this case PM10 concentration, close to the surface, probably related to this, let's say, stratification that we had in the morning. Here, let's say the concentration at 8:30 are still low, probably because in the morning people, when they wake up, they start with their heating system, and so we have a progressive emission starting from the morning, and these emissions then accumulate when the thermal inversion is present close to the surface. And then during the day, with the progressive arrival of solar radiation, the progressive stronger mixing which is present in the atmosphere, you can see that we have more, let's say, constant concentrations of PM10 along the whole vertical profile of this valley. So we have seen briefly what can be the effects of thermal inversions, and we have seen that thermal inversions can be stronger and they can persist longer in complex terrain than over flat areas. Then another peculiar meteorological phenomenon typical of complex terrain, in particular of mountain valleys, are the presence of thermally driven circulation. So we will talk a little bit about valley winds and slope winds and how these circulations can affect pollutant dispersion, pollutant transport. Valley winds are mesoscale circulations which are driven by thermal contrast between a plain and between a valley. In particular, during the day, as you can see in this image, in this scheme on the left, this panel A, we have that usually the temperature inside the valley becomes higher than the temperature of the plain. So this, you can see this red line represents the vertical profile of potential temperature in the valley, while the blue represents the vertical profile of potential temperature over the plain. And due to different reasons, again, we cannot enter too much into details, but also related to the different volume of the air inside the valley and above the plain, usually we have that the temperature in the valley is higher. So if the temperature is higher, it means that the pressure will be lower. And so we have a difference in pressure, especially close to the surface, as you can see here, this delta P, which will induce a wind which will blow from the plain towards the inner parts of the valley. These winds are also called up valley winds because they go from the plain to the upper part of the valley. On the other hand, during the night, we have exactly the opposite. During the night, usually the temperature inside the plane, so again, this blue vertical profile, so the temperature inside the valley, this red vertical profile, becomes lower than the temperature over the plane, this blue vertical profile, again, due to the fact that the cooling mechanisms are more efficient in valleys than over the plain. And as a consequence, we have the development of opposite pressure gradients. The lower temperature inside the valley, of course, will cause a higher pressure in the valley with respect to the plain. And so we have that the wind will go from the high pressure to the low pressure. And so we have this shallower, because usually the boundary layer is shallower during the night than during the day, thermally driven circulation, which blows from the upper part of the valley to the plain. And usually this circulation is called down valley wind because it flows down the valley. This is an animation of an idealized simulation that we performed with the weather research and forecasting model of, let's say, this thermally driven circulation over an idealized valley. Here you can see the two ridges, and this is the valley floor. You can see here the solutions or results every hour, and the colors represent the meridional component of the wind, so the south-north component of the wind. Red means positive wind, so a wind from south to north, and blue means a negative wind, so a wind from north to south. And it is clear the development of this circulation with during the day, this up valley wind, so this red, and during the night, the down valley wind, the blue. So again, during the day, the development of the up valley wind here, and during the night, the development of the down valley wind. So we have this reversal of the wind twice per day, with the reversal from down valley to up valley in the morning and in the evening. This is the same, but if here we are looking in the XY plane, here we are looking in the YZ plane. So this is a cross section of this idealized valley. Again, we are looking at the same variable, so the meridional component of the wind, the south-north component of the wind. And again, red means positive, so a wind from south to north, and blue means negative, so a wind from north to south. And also in this case, you can see, let's say, the presence of this red during the day, and then during the night, the development starting from close to the surface of this down valley wind. So this down valley wind at night and the up valley wind during the day. So it is clear again the transition and the presence of these two different circulations. Then here we have talked mainly about this along valley circulation, this up valley and down valley wind, so which blows in the along valley direction, along the main axis of the valley. However, in the valleys, we have also the development of cross-valley thermally driven circulations. In this case, due to the heating of the sidewalls during the day, so the heating of the sidewalls during the day will cause the development of upslope winds in the cross-valley direction, so winds which blow from the valley floor to the upper part of the sidewalls, as you can see in this image. But then during the night, and you can see also here in these other, let's say, results of simulations of idealized valley. So you can see that close to the surface, we expect the development of this upslope circulation, which of course can transport pollutant from the valley floor to the upper parts of the valley sidewalls. While during the night, then I will show you, there is of course the opposite, because during the night we can have the development of cold air close to the surfaces, as we have seen before. And so then this cold air will flow down the sidewalls and then will accumulate on the valley floor, causing the development of stronger thermal inversions. Again, these are the results of simulations performed with the weather resilience forecasting model for the same idealized valley, but here we are looking at the west-east component of the wind. So red means positive, so wind from west to east, and the blue means negative, so it means a wind blowing from east to west. And again, it is clear here the change in the wind direction. Here we are at noon. So at noon we have an upslope circulation because on the eastern sidewall of the valley we have this wind from west to east. So this is an upslope wind blowing from the sidewall, from the valley floor toward the sidewall, and the opposite occurs of course, on the opposite side of the valley. So with this negative wind, so an easterly wind blowing again from the valley floor to the upper part of the mountain, and the opposite, of course, on the other slopes of the mountain. And then during the evening we have the transition, and so during the night we have exactly the opposite situation with this downslope circulation, which blows with air which blows from the top of the mountain to the sidewalls. And again, we can see the same, but looking in the cross valley direction. And also in this case, you will observe this upslope circulation during the day, and then the opposite here, the downslope circulation during the night. So here we are positive on this western sidewall, so it means downslope, and the opposite for this other slope, so the eastern slope, the eastern slope. If we move then during the day, you will see the transition with this positive circulation or upslope circulation during the day. And so if, let's say, we want to sum up what we have seen related to these slope winds, we have that during the day, so here we have during the day, we have usually the development of this upslope circulation, which then can transport pollutants from the valley floor, for example, towards the upper parts of the mountains. So we have that, let's say, for example, here we have that the green line represents an example of concentration of pollutant, vertical profile of concentration of pollutants, and theta represent the vertical profile of potential temperature. Here, during the presence of these circulations during the day can enhance the transport of pollutants along the sidewalks, but also can mix pollutants inside the boundary layer. So you can see that usually we can have more or less constant concentration of pollutants inside the boundary layer. While on the other hand, if we concentrate on the nighttime phase, so when we have this downslope circulation with the presence of thermal inversions close to the surface, we can have different and more complex concentrations of pollutants. So the presence of the thermal inversions, as you can see here, if you look at the red line, so the vertical profile of potential temperature, but also usually higher concentrations of pollutants close to the surface, which are, of course, concentrated due to the presence of these downslope winds and the stable thermal stratification. So pollutants more or less are trapped close to the surface, and so they stay where they are emitted. And this is another example of the effects of these circulations, again, looking at some idealized simulations. Here we had, from this paper, Wagner et al. 2015, the authors released a passive tracer in this box. And here you can see the travel of these, so the different trajectories of these pollutant emitted here in the, let's say, at the bottom, at the mouth of the valley. The different trajectories are colored according to their altitude relative to the height of the boundary layer. And you can see that this pollutant is transported both along the valley due to the along valley circulation. And this example was during the day. So we had an up valley wind which transport, for example, pollutant from the plain to the inner parts of the valley. And they are also transported along the sidewalls due to the upslope circulation. So we have this different transport both in the along valley direction and in the cross valley direction. So it is clear that this kind of circulations can affect pollutant transport. As also pollutants which are emitted on the plane can be transported inside the valley due to these particular thermally driven circulations. And this is another similar example from another paper by Henri Diemot et al. 2019. Here I move to this website where there is the animation, so the supplementary material, let's say, of this paper. In this paper, the authors simulated the effects of thermally driven circulations on aerosol concentrations again in an alpine valley. In this case, it is the Aosta Valley, which is located in the northwestern Italian Alps. And here you will see that if you look at the hours during the day, we have an increase of aerosol concentrations inside the valley and in general in the mountainous regions, because we have this transport of pollutants from the plain to the valley to the development of this up valley and upslope circulation. So here we have the Po Valley in the southeastern corner of this domain, where of course we have a lot of pollutant emissions. And here we have this alpine valley, the Aosta Valley, where actually pollutant emissions are present, but not so strong as in the Po Valley. And you can see that even if we don't have a lot of pollutant emissions in the Aosta Valley, we have this increase during the day of the concentration, you can see, following this diurnal cycle of thermally driven circulation again. And then during the night, we have the opposite. And so you can see how these up valley winds can transport pollutants from the plain towards the inner parts of the valley. So they are for sure very important for determining pollutant concentrations in alpine valleys. And this is another example that I wanted to show you. This is another particular up valley circulation which develops in the valleys around the city where I live. I live more or less here. Trento is located here. Now I am here. The university is on the eastern side of the valley. This is Lake Garda, which is the greatest Italian lake, which is located at the end of this valley. During the day, we have the development of this up valley circulation, which is actually a mix between a lake breeze and a valley wind, which blows from the lake towards the inner parts of the valley. Here I'm showing an animation of different webcam images in which you can see the effects of the transport induced by this lake breeze. So we are more or less here and we are looking towards the lake. Here in this background part of this image, you can probably see a little bit of Lake Garda. Here we are not looking actually at transport of pollutants, but a transport of water vapor. But it is, of course, the situation is more or less similar. So the equation of transport for water vapor is similar to an equation for conservation of a pollutant. And this is a sort of tracer, and you can see during the day, due to the development of this up-valley wind, the arrival of moisture air from the lake. So you can see both the arrival of this moisture air, which is transported by this southerly wind, so the up-valley wind. And also you can see the effect probably of the deepening of the atmospheric boundary layer. So this moisture air is also gaining altitude during the different hours due to the fact that we had a deepening of the convective boundary layer starting from the morning and arriving in the afternoon, because the first images are at 9 in the morning, then 10, and here we are 11 in the morning. So we have the progressive arrival of this wind, which can transport. In this case, we have mostly water vapor, but the same, of course, can also be present if we have transport of pollutants from a plane. And this is another example of the combined effects of thermal inversions and valley winds. Here we perform measurements again inside our valley, again in Alpine Valley. And in this graphic, you can see in the x-axis time, so different days in winter. And again, on the y-axis, we have a height above ground level. The black continuous line represents PM10 concentration measured during these days, and the colors represent the wind speed measured with a SODAR, so an instrument, a remote sensing instrument, which is able to measure the vertical profile of the wind during these different days. You can see, I think, clearly that we have this cycle in most of the days of wind, because usually here, at least in the Adige Valley, we have a stronger up-valley wind, so in the central part of the day, and then usually a weaker down-valley wind. So we have this cycle with stronger and weaker winds. And if we have this cycle of winds, usually we have lower concentrations of PM10. Then you can see a period starting more or less from 13th of February and arriving at the 17th of February, in which we have a progressive accumulation of pollutants on the valley floor, arriving at a rather high concentration of PM10. This is what typically happens in alpine valleys when we have the development of thermal inversions, which can be persistent. Here we don't have, let's say, a graphic with the vertical profile of temperature, but these were days characterized by thermal inversions and weak winds. So if we have both thermal inversions and weak winds, of course, pollutants tend to concentrate, to accumulate close to the surface. And so we have this progressive worsening of air quality conditions. So we have a progressive increase of, in this case, PM10 concentrations. Then here we had, you can see an episode with strong winds. Actually, this was a mix between thermally driven winds and the wind caused by synoptic effects, which you can see decreased the PM10 concentration. So this wind broke up the thermal inversion, so this situation with reduced mixing, and also transported pollutants away from this location. So you can see, let's say, the combined effects of thermally driven circulation and winds, and the presence of thermal inversions, in particular during winter. Finally, the last part of this presentation, I wanted to show you the results of an experiment that we performed again in the city of Bolzano, in this Alpine Valley, to evaluate the dispersion of pollutant from the incinerator of the city. So you can see this is the incinerator of the city, which is located in the southern part of Bolzano. And the aim of this project was to evaluate the fate of the pollutants emitted by this incinerator. So this is the location. We are in northern Italy here. These are the, let's say, the valleys that we are investigating. This is a zoom on the city of Bolzano with different valleys joining here. So a very, very complex terrain. And the incinerator of the city is located more or less here, so in the southern part of this urban area. We already talked about this, so here we have to take into account all the aspects that we have introduced in this brief seminar. So the effect of local circulation, so thermally driven winds, the possible presence of thermal inversion, because we perform this experiment during winter, which can affect reduced mixing, which can induce reduced mixing. And then we can have also the effects of upper level winds. So we can have also synoptic winds or large scale winds, which can affect pollutant dispersion. In this experiment, in order to understand the fate of pollutants emitted by the incinerator, we perform an experiment with a passive tracer, sulfur hexafluoride, because, of course, let's say the incinerator emits pollutants, but these pollutants are emitted also by other sources in this valley, in this basin. So it is not easy to discriminate what type, if, let's say, the PM10 concentration that you measure or the nitrogen oxide concentration that you measure are emitted by the incinerator or the other sources which are present in the basin. So we performed this experiment putting SF6, this sulfur hexafluoride, inside the chimney of the incinerator, because in this way we were sure that the SF6 measured in the basin was caused by the emissions from the incinerator, so the plume of the incinerator, and not by other sources. So we performed this experiment with 2 releases of SF6, and then we measure with these bottles the concentrations of SF6 that then were analyzed in the laboratory. At the same time, we perform meteorological measurements to evaluate meteorological conditions during this experiment. So we had a SODAR on the roof of the incinerator. A SODAR is an instrument which is able to measure the vertical profile of the wind. We have also a LiDAR, which is a similar instrument for measuring the vertical profile of the wind, which was located close to the center of Bolzano, here in this Chan dot. And then other, let's say, normal weather station, and the temperature profile to also evaluate the stability, the thermal stratification in the basin, again, close to the incinerator in the airport of the city of Bolzano. Here in this situation, we had a peculiar local scale circulation, which is a down valley wind, which is present in this along this valley, this secondary valley, which joins the basin of Bolzano, which is this is the main valley, this is the secondary valley. At the end of the secondary valley, we have in most of the night a very strong down valley wind, which arrives over the city of Bolzano. And so this wind, of course, can potentially affect the dispersion of pollutants of the plume emitted by the incinerator. And actually, we evaluated that there can be 2 different situations looking at the interaction between this down valley wind and the air inside the basin of Bolzano. You can have a situation with a strong thermal stratification, so a strong, what we call also cold pool, so a layer of cold air close to the surface, so a strong thermal inversion in the basin of Bolzano. In this case, the air coming from the Isarco Valley, which is this one, this is a section from the Isarco Valley towards the basin of Bolzano, floats above this cold air because it is warmer, so it is not able to reach the surface. And in fact, if we look at these maps obtained with a meteorological model, you can see that the wind is clearly present at 950 hectopascal, so more or less 200-300 meters above the surface, while close to the surface at 10 meters above ground level, the wind in this situation is very weak in the basin of Bolzano, simply because this circulation is not able to reach the lowest layers due to this strong thermal stratification. So in this case, we have that when we have this basin cold pool, and so the temperature of the basin is lower than the temperature of the wind, the down valley wind arriving in the Bolzano basin, we have that the wind floats above the cold pool, and close to the surface we have very weak winds. We have an opposite situation, in a situation in which we have, on the other hand, no strong thermal stratification in the base. So here we have the same section, and you can see that here we have a higher temperature close to the surface. In this case, the down valley wind is able to reach also the ground. So with, of course, potentially completely different effects on pollutant dispersion. So this is the wind at 10 meters above ground level. And again, this is the wind at higher levels above the basin of Bolzano. This is another day in which we perform these measurements, these simulations. And so in this second case, we have the situation in which the temperature in the basin is higher than the temperature of the down valley wind arriving from the Isarco Valley, the secondary valley, and so the wind is able to reach also the surface. And then we performed, in order to evaluate the effects of all these different phenomena, the effects on pollutant dispersion, we performed 2 releases of SF6. One in the morning, as you can see here, with stable stratification, in particular close to the surface, and one in the afternoon with a more unstable stratification. So to evaluate pollutant dispersion in 2 different situations, and 2 different situations also considering wind direction, because the first release, which was here, was performed in conditions with northerly wind. So this is the wind measured by the SODAR at the top of the incinerator roof. So again, we have a time height plot. The first release was performed here with this northerly wind. You can see wind from north. And the second release was performed here with this wind from south, because we have the transition from down valley to up valley wind. So we have completely different situation, both considering the stability, more stable conditions in the morning, unstable in the afternoon, and the wind speed and direction. So wind direction, in particular from north in the morning and from south in the afternoon. And these were the results of our experiment. So here we will see different points which represents the different samples, the different bottles that we collected with the concentration in ppb, parts per billion, of SF6. This is the first morning release, so you can see here we are in the morning, 10:30. In the morning, due to the strong stratification, the fallout, the presence of ground concentration, the measurement of ground concentration was delayed by more or less 2 hours after the release, because of course if we have a strong stable stratification, the pollutants which are emitted by the chimney, with considering also the plume rise, remains, let's say, confined at higher levels, and they are not able to reach very easily the surface. And so probably in this case, we had the stronger concentration along the sidewalls, where the plume hits the sidewalls, but lower concentrations close to the valley floor. And in fact, you can see that the highest concentration were measured here, close to the incinerator, which is located here, and a little bit south of the incinerator, due to the presence of the northerly winds. After more or less 2-3 hours after the release, we measured 1.2 more or less ppb close to the incinerator, probably due to the fact that in the late morning, due to the establishment of more mixing condition, this SF6 was able to reach also the surface due to the presence of stronger vertical mixing. Then, if we wait a little bit, we will see also the effects of the release in the afternoon. The release of the afternoon was in the early afternoon, and immediately after the release, due to the presence of the unstable condition, the pollutants reached the surface. And you can see that north of the incinerator, which is located here, we measured higher concentrations of SF6, in particular here very close to the incinerator, 12 ppb of SF6. This is of course because with unstable condition we have more vertical motion, so the plume is able to reach the surface more easily, and also this arrival of the plume at the surface is faster, and so with also higher, in this case, higher concentrations. And so you can see in particular how thermal stability and different valley circulations can affect both the locations and the strength of pollutant concentrations emitted in this case by the punctual release as a plant. Finally, we perform also simulations of this event. We used two completely different models, actually CalPAF, which is a very widely used model also for regulatory reasons. Is one of the model approved by the Environmental Protection Agency of the United States. It is a PAF model, so it means that I don't know if you have treated PAF models in the other lectures, but it means that puffs emitted by a certain source are advected with the wind, while diffusion is treated as Gaussian diffusion. So we have an increase of the size of the puff following Gaussian dispersion, typical Gaussian diffusion, Gaussian dispersion process. On the other hand, we perform also simulation with Lagrangian particle model called SPRIWeb with different parameterizations, but we are not entering into these details. Lagrangian particle model is a completely different model, let's say, because it treats each, let's say, particle in a separate way. So each parcel emitted by the source will follow a different path and will be affected by the mean wind and the turbulence which is present in the atmosphere. And here I want to show you these results to show you that, let's say, the very widely used CalPAF model is actually not probably the best tool to evaluate pollutant dispersion over complex terrain, in particular if you want to simulate a particular episode and not, for example, deriving an average concentration of pollutants over a long period, because the assumptions that are performed, in particular considering Gaussian dispersions, are not considering the proper effects of the complex flow field that can be present, for example, inside a mountain valley with the different circulation that we have seen before, both along valley and cross valley circulation. So here we have an example of what CalPAF simulated in the morning, so after the first release of SF6, and in the afternoon. So a very, let's say, smooth plume, which is not very representative of what happened in the reality. On the other hand, on the right, sorry, you can see the same results, but obtained with one simulation with the Lagrangian particle model, SPRIWeb, and you can see that we have a more complex behavior of the plume, which is emitted by the incinerator. And actually here, I don't have time to show you the details, but we also validated the results of the different simulations against the measurements that we performed. And it was clear the superior, let's say, performance of the Lagrangian particle model with respect to the CalPAF model. And finally, this is the last slide, just an animation of the simulation performed for the obtained for the afternoon release using the SPRIWeb model. And so you can see the emission from the incinerator, which is located here, which is advected first towards north due to the presence of the up-valley and upslope winds. And then the plume tends to come back towards the initial position, because then in the late afternoon, we had the transition from up-valley to down-valley wind. So you can see how complex can be the pattern of dispersion of pollutants over complex terrain. So this was the last slide. So I have more or less in time, and thank you for your kind attention.